think I had clicked on start and recording stopped in between. Yeah, now it's back up. Okay, let me quickly summarize so that those who listen to the recording get it also. I think the team server was probably loaded last time I clicked on start. It did not start actually. Okay, so just to quickly summarize, and in case you guys have any questions, you can state it on chat. So what we went through is we are discussing message passing primitives, what we did last time, but we are elaborating this little bit further to say there are two types of message passing operations. One is non-buffered and blocking, and this we will see that leads to idling problems, and we will later see in a deck that it leads to deadlock issues as well. And most of the time when you use some sort of a communication send receive between processes on different nodes, you will introduce some kind of buffering. You will also introduce non-blocking, and we will talk about that later. But essentially the purpose of buffering is you remove the idling part, right? So it will not appear that you're wasting time waiting to copy data while the application program does nothing else. And we covered this situation where if you really want to do non-buffered blocking, the most extreme case of being very conservative in making sure sender receive synchronization happens. So there are three cases. Either sender process comes first and is waiting. So waiting means this white patch, right? Where sender is busy, then the sender sends a request to receiver. Receiver doesn't respond, and the sender is actually waiting because it's a non-buffered blocking. And once the receiver is okay, data transfer happens and they all go busy again. So gray patches are the busy periods doing useful work. Black is data transfer and white is that process is not doing anything. So either sender comes first or in the diagram C, receiver comes first and waits for the sender to send something, right? So in this case, it's a receiver idling. And only in some rare situations, it may happen that both come at the same time and there is no idling. They are perfectly synchronized to start sending and receiving data. But this may not happen. And for this specific reason, why most of these protocols or libraries that you will use will kind of make sure there is software level buffering, and most of the time hardware itself has some buffering. So buffering is basically to alleviate this idling time. So that's when we were talking about the slide 9, where if you look at the left hand side, this is the network card itself having some sort of a buffer. So sending process comes and sends and keeps doing its own work, and locally that buffer is getting copied. The data is getting copied into the buffer, and data send may happen later from the network card. The application is not kind of waiting for that data transfer to happen. Same thing with receiver. If receiver comes first, maybe it's not yet sorry, the receiver is busy doing some work and receiver is not yet ready to receive data. That's also perfectly okay, because the library will actually take the data. It will make sure the data is sitting in a buffer, and when the receiver process is ready, it will start consuming data from the buffer. Now, uh, it is possible that the buffer is not in hardware. Extremely rare case. Most of the systems nowadays have sufficient buffer on the communication hardware itself. But assume if it was not there, in the absence of any communication hardware which has all this buffering, then you have to do interrupts. Uh, this is typically in old systems. I don't think it is done in any of the modern systems where, let's say the buffer is not there. So what the sender process will do is it will call the operating uh, system called to send data, and the the primary application process will get interrupted. It will stop, and the send will actually happen to the receiver side. The receiver process will get interrupted. It will stop, and data will be copied into the buffer of the receiver, and then both parties can continue. And at some point of time later, when the receive comes in, it will then take data from the software buffer, right, and start processing it. You see that here, essentially you need interrupts. You need to interrupt whatever the sending process and the receiving process are currently doing and engage in a communication. and receive can come much later. So you have to have some kind of software buffer inside the library that keeps the data while the receiver is doing its own work. When receiver is ready to receive, it will call the receive and get the data from there. But again, you will mostly encounter the first case, left hand side case, as you write your programs. There are network cards which anyway will do all this buffering. Now, the problem with buffering that you will often encounter when you write these parallel programs and moving around a lot of data, that's why when you're doing an assignment, you'll get a good flavor of large sends and receives. Often what you encounter is that your buffer sizes are bounded, right? If I go back to the previous chart which talked about send and receive, you see here I'm declaring a buffer, right? I'm telling you this is my send buffer and this is my receive buffer. What if the sender sent you data that is not holding in the receive buffer? Then what happens? Right? So these are issues you might encounter where buffer sizes are bounded, and because of this, you may have a significant impact on performance. So you cannot like send large chunks of data in one shot. You may have to be cognizant of the fact that the sender and receiver have limited buffer sizes, and then keep iterating to say, let me send 1 megabyte at a time because that's my buffer size on either side, right? So you may have to iteratively send, let's say you have to send a gigabyte of data in your analytics program. You have created a partition of 100 gigabytes to put on 100 nodes. So each partition is 1 GB, and you can't make a single send call to send that 1 GB data because you don't have that much buffer. So you iteratively kind of send that data, maybe 1 megabyte or 10 megabytes at a time to send 1 GB. Problems you will often encounter are what if the consumer is much slower, right? So you are putting data in the buffer, but receiver is not fast enough to pick it up, right? So consumer or receiver is slower than the producer. Again, think of the context of your assignment. I have to have a master node which takes the data, partitions it, sends it to all the slaves. The slaves are not fast enough. So they're not receiving partitions at the same rate as you are sending them. So then you have to build enough fault tolerance into all this to say that, okay, let me a throttling to say that let me send chunks of data. If consumer is slow, let me throttle it and wait, right? I have to put pauses in between. So you will probably not in this assignment, but in real life, when you write a much larger scale program, you'll get the understanding that it's actually not so easy to do all this communication. And not just consumers being slower than producers, but also what if suddenly the consumer dies, the slave node gets killed, software problem, hardware problem, whatever, network issue, then where do you start again from, right? So fault tolerance, all these things will be harder. Now, I want you to do the OpenMPI based assignment because you will actually use this basic send and receive calls to move around data, but I've not asked you to make sure you handle throttling problems and when consumer process dies, what happens, because then you will realize that it's very difficult to write some of these programs from scratch, right? Especially in the case of faults and slow processors and all that. That is why we appreciate later that systems like Hadoop, Spark, this kind of middleware make a lot of sense because as a programmer, then you don't have to do all of this. There's already a middleware in place which will do this, and you can only focus on the logic on top. Right? Now, the other thing that might happen is deadlocks, right? So even if you do buffering, because buffering is only removing the idling part, right? You're buffering, hence your application is not waiting till you copy data into the operating system and send it out on the network link. But buffering does not solve your deadlock problem. So look at this code snippet of two processes, right? They are exchanging some data. So first process P0 does a receive. It wants to read some data from process P1. And then as a response to the receive, it wants to send data to process P1. On the other side, process P1 also wants to receive some data from process P0 and then send data to process P0, right? Both want to receive data from the other and then send. Now it depends on the timing of all of this. When did you start process P1, P0, and what data and all that they want to exchange? You may end up in a deadlock because if the receive is blocking, right? Remember, it's we are talking about buffered and blocking. So buffered solved the idling problem but did not solve deadlock problem. So blocking means now you went to receive data, but the send is later. So P0 will block. This receive will be blocked. It will wait for data. But P1 is not sending anything before it receives. Similarly, P1 also wants to receive, but send comes later. So P1 will also wait for P0 to send something. So either of them will wait on the receive call and nobody will do anything. It will be a deadlock. So it's a cycle. One is waiting for the other. So if you do blocking message transfers, this is likely going to happen. The processes might wait in a cycle, waiting for data from each other. So that is why non-blocking kind of primitives are also introduced. I'll give you an example in OpenMPI where non-blocking is also used. But there you have to be a little careful, right? If you do non-blocking, that means you're triggering some sort of parallelism within that particular process, right? You should make sure that it's semantically safe to do that. So for example, here, P0, I make receive as non-blocking. Now, it's good that A and B are different variables. What if it was sending A? What if it was like this? Suppose there was another process. Uh, let's put it here. Let's put another process here called P2. And let's say, just making it up, let's say this send was sending data to P2, right? And it was sending A. So this was to not to process 0, I'm sending to 2. What if I did it like this? Now my semantics, what I meant was you receive data from P0, put it in variable A, send that variable now to P2, that value to P2. But now if you make receive non-blocking, I have not even received that A data from P0, right? Let's say I have already initialized at P1, my value of A was equal to 1, right? But what I was sending here was not 1, it was some other value. So I'll end up sending 1 to P2. But if I make it non-blocking, I may send A equal to 1 to P2. But suppose from processor P0 or process P0, if I had received A equal to 2, then I'd have received the value 2 to P2. That's what I meant actually, but because of asynchronous, that behavior changed. Maybe semantically is not the correct thing to do, right? So be careful with asynchronous because the following steps may be dependent on that receive. In that case, your program may not be the correct one just because you wanted to get better performance. You did asynchronous, but may not work, right? So make sure that it's semantically safe to do asynchronous. And typically, when you do non-blocking, uh, you have to check status. Like I called a receive, didn't happen, so I proceeded. I have to go back and check, or I have to set some kind of a callback to make sure that when I receive data, I get notified. So this asynchronous programming is a little tougher to do, right? Because and if bugs happen, it's actually more difficult to debug all of this stuff. But when it is used correctly, it's a very good mechanism, right? Because you're overlapping communication overheads with useful computations. Right? So while data was getting received from P0 to P1, if this was asynchronous receive, I would have proceeded with the following pieces of code while I was receiving data, right? So some overlap would have happened and I would have gotten better usage of the compute resources. So this is again an example of non-blocking, right? So imagine I called send from the sending process here. This is left hand side. Let's talk about one where there's no hardware support or the one with hardware support. Hardware support just means that there is a buffer, right? So buffer is in the networking card. So let's talk about the right side because that's more realistic. All your communication hardware have buffers nowadays. So When you send, you see that the program still proceeds, right? Under the covers, the request to send is getting done, and then the receiver is okaying and data transfer is happening after that. But you as a application program, you're not blocked, right? You keep proceeding. You see this gray line here, I mean, it continues to work. So just to be very clear, uh, the timeline is like this, right? Time is flowing this way. So, and this gray parts is useful computation that the sending process is doing or receiving process is doing. So nobody's blocked. They're proceeding. They simply called a send and it's happening in the background. Only thing is you have to be very careful, as I said, with it's unsafe to update data being sent, right? Also make sure on the receiving side that you're not kind of reading, you're not using data that is not completely read, or data that is getting received, or you're not using the data that is supposed to be received but it has not been received yet. So that depends on uh, the ability of the application programmer to make sure that they do these things, right? Uh, so that they don't end up corrupting data with asynchronous sends and receives. Again, in the context of your assignment, I'm happy with if you make blocking send and receive calls. Uh, that will waste some time in data copying, but the goal of this assignment is to make sure you know how to write your first parallel program, not about squeezing performance out of it. But you will appreciate that in a real system, you have to do some of these performance improvements. And that's where programming programs become a lot more complicated. And that's where you kind of wish that you had some middleware, that you don't have to write all of this. You're a data analytics expert writing some algorithm. Why are you bothering about whether you're doing communication properly? Right? So these were a few flavors of buffering and non-blocking that I left out in the last session. I think we talked about this also. So then we started on MPI in the last class, and in MPI, I skipped a few advanced features in MPI. So let's talk through that. I hope you have started installing and using OpenMPI. Again, you can use any language that is supported that has a MPI specification. We talked about the 6 minimum set of routines with which you can get started in writing a program. So I won't repeat any of that. Uh, let's see, I missed probably a couple of things. Yeah, so this is the sending, receiving messages, data types we had covered. We had covered all of this. Deadlocks. So uh, let me bring back something similar to the previous example, but specifically in the MPI context, how you can end up creating deadlocks. So imagine that the same scenario as this particular one that we talked about. Where is that short program? No, this one, right? This one, which I was kind of talking about, right? Both of these may get deadlocked because this receives and sends, right? So this was the changes I was making. Let me remove that. And this was sending B. Yeah. So this was deadlocked. So let's take this similar kind of example and look at OpenMPI program. This was my OpenMPI program. So there are two processes, right? So when I say my rank 0 and my rank 1, that means I want this piece of code to execute for process P0, else this is the piece of code to execute for process P1. Now, in this case, what has been done is this does a send, these does two sends, and this does two receives. And if you do blocking, let's say this is sending A and this is waiting for a receive of B, right? Then it's sending B and this is waiting for a receive of A. And when you do something like this, it'll end up in a deadlock because this is waiting for different things from different processes, and a send will not be able to a send completes but a receive will not work, and a receive because if the receive doesn't complete, the next receive also won't be called, right? So these will end up If MPI send is blocking, this will end up in a deadlock situation. We can actually try combinations of doing in the previous program a receive here, send here. We can try that out also. I want to send a variable to this and sorry, receive, and then I send, and here also I wait for a receive of B and I do a send. This will also create a cycle. This will get blocked. Now, let's look at this case. In this, there are multiple processes and they are going in a cycle sending, receiving data. So here I don't have two processes. I may have any number of processes, but if you see the code, essentially what I'm doing is I'm sending data to my neighbor. You see my rank plus one. So I send data to, let's say, to my right neighbor, and I receive data from my left neighbor. Right. So uh, now if you do something like this, you can see that I'm going to, if I do blocking sends and receives, this automatically creates a cycle, right? So this will be like you can keep processes in the circle, and essentially what will end up happening is this particular process P1 will do a send to P2 on this side and will wait for a receive from P3, right? So you will end up P1 pointing to P2 because it is sent something, P3 pointing to P1 because there's a receive edge, and this will end up in a cycle. You can easily see that P1 will block for P2 send, P2 will send to P3, and P3 will send to P1, and P1 is waiting for P3. So all of them will end up waiting for each other because you have a send and a receive in a cyclic order. And whenever you create a cycle like this, it will lead to a deadlock. And this deadlock happens primarily because you're calling a blocking send. The way to end up kind of avoiding this kind of a deadlock situation is if you break the cycle. So here is a way you can try this out uh, in your OpenMPI code. This is a code snippet you could take and modify and run. If you somehow don't send to your neighbor, you see that I'm not sending it to my neighbor. I'm actually only communicating between the odd processes and the even processes just to break the cycle. So even though the sends, so if my rank mod 2 is equal to 1, that means I'm an odd numbered process. So the odd numbered processes basically send data to the even numbered processes. So send happens to the even number and receive happens from the even number. And else, that means if I am an even number process, then I will communicate with the odd numbered processes, which is my rank minus 1, my rank plus 1. That way, you will end up breaking the cycle. So let's take P1. If P1 is odd number processes, I will actually not communicate with P2. I will do send and receive with P3. In that case, a cycle will not happen. You can always put more nodes on this and make it clearer. But essentially, just break the cycle by not talking to your immediate neighbors, but let an odd talk to even and the even talk to the odds and doing send and receive. In that case, you will not end up waiting on each other. So basically, your attempt is to break a cycle. So this is one way, but there would be other ways also. So here I'm still using blocking send and receive and just creating a topology where cycle doesn't happen. This is an optional message you can sometimes use, which is a single call you can make a send receive, but I mean, it's not mandatory you use it. This is not a necessary thing. So a better way, instead of doing this topology change I just said, so to kind of make sure that you don't end up in a deadlock, another way to do this is non-blocking send and receive. So there is a variation in OpenMPI uh, because it's part of the MPI spec. It's called I send, I receive. So this is your non-blocking option. If you do this, instead of send receive, do I send or receive, that means nobody will block on each other, and that's when deadlocks will not happen. But again, you can realize that you have to be a careful programmer, right? Make sure that you don't modify data as it is getting sent or received, or uh, you basically make sure that the data that you have not received yet, you don't start working with it, right? The dangers of asynchronous programming. But this is a good way to avoid deadlocks. Because it is non-blocking, there's no way anybody can block on another node or another process. So no question of a deadlock happening. Of course, when you have asynchronous non-blocking, you must have a way to test if the operation actually finished. So there is an MPI test function as well. Uh, you notice that there's an additional parameter attached to any asynchronous request, which is pointer to the request, right? So this is basically what is used to check status. So I can call an asynchronous receive. That means the request will be actually the pointer to the request will be given back to me here, and I can use that pointer to test the status of whether that receive or a send actually finished, right? So you could separately go and keep testing with your send and receive is finished. You should put that check, because unless you check, you should not use that data. So only when your status returns that actually the data was received or sent, then only it makes sense to use this buffer, right? So don't touch this buffer as send is happening or as the receive is getting finished to fill up the buffer. Don't touch this buffer. And the way to determine that is make sure you keep testing the status on the request that was made for the send and the receive. That way you will avoid all the semantic problems of corrupting those buffers as data is getting sent or getting received, right? There's another way, of course, also to wait. There is a way to kind of uh, you can wait for the operation to complete instead of kind of polling or checking on the status. You can call an MPI wait function with this request and the status, and this wait will unblock when the status changes, the operation is complete. So these are some advanced ways of introducing asynchronous programming in OpenMPI. So you can use that isend. So if you simply replace isend here, this call will not, this will never lead to a deadlock. Okay. There are a couple of other primitives out there which we had used in our program for collective communication and computation. So I'll briefly touch upon those. Uh, so in the code that I've shared with you for the pi computation, I'd use something called a broadcast and a reduce, right? So what they do is basically outlined here. Uh, so when you do broadcast, essentially it's about sending the same data or the same buffer. Instead of calling send one at a time, using one function call, you can send data to the entire communication domain, right? And reduce is an interesting operation. Reduce essentially does some kind of operation, well-defined operation on the send buffer and puts the data in the receive buffer. So what happens is every process will call this reduce. So this is parallel processing happening. So every process has some data in the send buffer. So it will basically call this input data in the put this input data in the send buff, and the output will come in the receive buffer. So let's say you want to do a, if you look at the pi example, I was doing a summation, right? So I could essentially do a addition operation where I want to add 10 numbers by simply calling an MPI reduce with each process contributing its own number, and the result will be actually put, the addition of all the numbers will be put in the receive buffer. And I can specify the operation to be an addition operation. So it's interesting shortcut where you don't have to write code to say, let me receive data from all these processes, and then let me put it on one machine, let me add up all those numbers, and then give it to you. I can simply call reduce, and the library takes care of gathering, doing the operation, and gathering all the data and putting it across to the user program. So broadcast is sending one to many, and think of reduce as the opposite. It's gathering all the data and putting on one node. But in the process of reduction, it can also do some computation. So this op is basically the computation on the different data that it gathers and puts on one node. So what kind of operations can be done here? So these are your predefined reduction operations. You can do addition, min, max, product, various logical operations, bitwise logical operators you can do, some max min. I'll show you one example of this. So all these operations are pre-built into OpenMPI as a reduction operator. So you can use this shortcut, otherwise you have to write more code to add data or multiply data or do max and so on. So this is a more optimized communicator for broadcast and reduce. There was one more thing there called barrier. I don't know if you've heard about this term barrier synchronization in programming earlier, but barrier essentially means if you put this line, this one line MPI barrier and the communication domain, let's say communication is all, right? That means all the processes. Let's say I have 5 processes. Now what I want to do is these 5 processes are proceeding in parallel, but I want them to synchronize at a certain point, which means let's say all of them are doing some data manipulation. When all of them are done with the data manipulation, I want all of them to stop at some point. Let everybody come to that same point, and then let's proceed. So if I let's take an example of let me try to show this to you in some kind of a diagram here. Let's say this is my timeline, right? And all these processes are going on. So this is one process which has finished its work and it's done at the end of the arrow. There is another process which is still working, but it finishes here on the timeline. There is another process which uh, has finished even earlier. Let's say it's finished here. They all started at the same time. I forked off bunch of processes. I somehow want all these processes to kind of synchronize at a certain point in time when all the work I've given them is done. So if you take this line, this is a point where all of them are practically done. But how do I detect it? How do I tell them to stop and synchronize? So if you put this line MPI barrier and the communicator means I have to know which processes should synchronize, right? So that's the communicator is these 3 processes. So if I call MPI barrier in each of the code, let's say it was doing some computation C1, C2, C3. End of the code, if I put MPI barrier, that means all of them will hit that MPI barrier library call after they finish their own work, and then they will wait till others also reach that point. So it's like a finishing line. Everybody synchronizes at the finishing line. So whenever MPI barrier is called, let's say this particular uh, process actually finished here, but it's not going to proceed with the rest of the program. It's going to block here and wait till it reaches here. He's going to wait, right? This is the waiting time. So, and then MPI library will communicate between the processes and tell them that, look, now everybody has reached MPI barrier. Now you can proceed with whatever else you have to do. So it's a good synchronization mechanism. So I think keep these 3 in mind. These are very useful for parallel programming for some kind of collective communication. The first one is about how do I know everybody has reached this point where I am? So You can put some code right after MPI barrier, and you know that code will execute only when everybody else reaches that point. Uh, Broadcast is one to many. I want to send some piece of data to everybody. And reduce means I want to gather data from everybody in my communication domain. And by the way, as I'm doing it, I want to perform an operation, a reduction operation to come up with one number. Right. So these three are good ones to remember. Uh, this last one, max lock, min lock, I put in an example here. Uh, this is also a good way to kind of do a max min, but essentially, along with the numbers, you also want to know uh, which process has the minimum number. Let's say I'm calculating min. Now the minimum value is 11 here, right? Now I also want to know not just min 11, but I also want to know which process has that particular number. So if I call min lock, then the return will be 11 comma 2 because second process which has the 11th number. Very good for searching. So if I want to write a search application uh, and I want to find certain numbers, I don't want the value to be searched only to say the value exists. I also want to know where it is found, right? Let's say I'm searching through a distributed database. Let's say these are all database processes spread across nodes, and I'm looking for where is the number 11. And if I call a minlock, it'll at least return to me, yes, the number 11 is found because it returns 11. And also it will return to me at least randomly one process ID where I found 11. And if it is found in multiple places, as you see here, I've noted down, then it will basically return me the smaller one. So 11 is found in 2 and 5. Actually, it's not random. It is going to return to be 2, the smaller index where the data is found. Right. So good way to do searching, parallel searches using this reduction operator. I had gone through this example of calculating pi. I hope you guys recall and you have tried running it yourself. I had used this broadcast and the reduction operator here. I wanted to use broadcast because I didn't want to write from the master node a send function to all the slaves, right? Otherwise, I would have put code inside my ID equal to 0. I would have put some code here and said send to process 1, send to process 2, send to process 3. I just did a broadcast of this n and it went to all the processes. Much simpler. Then I didn't want to go and sit and add individually all these areas, right? The individual results of all these boxes. I simply did reduce with MPI sum being my operator. So what happened was the individual contributions of pi from each of the data partitions got added up automatically in the code of the MPI library and the answer came back to me. Much simpler. I could have done it without reduce. I could have explicitly sent the the value of partially calculated pi to the master node with process ID 0, and I would have had some code sitting in process ID 0 saying, okay, let me start adding up all the numbers that are sent to me. So in your assignment, you could do something like that. You don't need to use reduce. You could actually receive data for all the partitions onto one node and do whatever calculation and present the result. But you can also try to see if you can use an MPI reduce and write smaller code. There is no example of a barrier here. I'll see if I can give you a barrier synchronization example somewhere. Okay, I'll take a quick pause to see if there is anything, there is a doubt here before I proceed with the multi-threading piece. All right. So let's go back from this distributed memory model where we were doing OpenMPI. Let's go back to a shared memory model. Essentially, that it means that the only way I can get parallelism is writing a multi-threaded program because threads share common memory space, right? So threads communicate by reading, writing shared variables. You can, if you've not done shared memory programming before, then essentially it's like a big bulletin board where everybody can write. So any thread can go and read data, write data from this shared bulletin board, which is like a shared set of variables. So think of an example here. Thread 1 is modifying X. Thread 2 is also working with X. So both will share this uh, variable X in the shared common memory address space. So if you have multiple cores on your machine, uh, share this memory address space, then so basically if you write a program that is a process, and within the process you have used a multi-threading library, then the entire process's memory is a shared address space accessible from any of the threads. So any thread can access the entire process's address space. So let me just put, there's no confusion. This is one OS process running on a node. Within the process you want to explore parallelism, you can use a multi-threading library, and all these threads are sharing the same OS process space and working with the common set of variables. Much lighter weight parallelism, but essentially you do both. You actually do multiple such OS processes, potentially running on multiple nodes. That's what OpenMPI is for. And within each process, you can always write a multi-threaded program to make things faster, right? Utilizing the multiple cores on the same machine. Now, thread is nothing but an instance of a function, right? So if I can do some matrix manipulation, we went through this last time, I believe. If I write something like this as a dot product, right? I have written a function, let's say called dot product, which generates each cell of C, right? Because I'm doing some dot product between or matrix multiplication. So I can take for row is equal to this, column equal to this, and calculate within the nested loop C is equal to row column, C row column, this particular index. I want to calculate dot product and get the value. Now I could potentially parallelize this, right? Using multi-threading. I could simply create a thread for each instance of the dot product function. So if I have to calculate a 100 into 100 element matrix, then potentially I can create 100 into 100 or 10,000 threads, and it should be faster given I have enough machine resources. So my potential parallelism could be a 10,000 independent threads, each calculating one cell of matrix C, right? So all the row column indices get created parallelly. Ideal situation, right? Given I have enough resources. Now, uh, essentially, the thread kind of programming is a more natural extension to sequential programming because you're not sending, receiving messages. You're working with variables like you do in sequential programming. Only thing is the variables can be parallelly accessed by different threads. That's the only bigger issue here, right? That any thread can read write to shared variables. But it looks naturally kind of natural progression from the way you write a sequential program. Of course, it needs some hardware support because what's the point in running multiple threads if the hardware does not run multiple threads? Because then what will happen is you have a one core machine with one thread. You have written a multi-threaded program and all the threads run on the same core. Nonetheless, it will give you some benefit because when you're running one thread, maybe it is doing some IO, so it is blocked, or it is doing some memory access. So maybe the second thread can pick up and start using the processor, right? So you will still get some parallelism, some benefit of multi-threaded on a single core, but again, not worth that much. You'll do some kind of latency hiding, but typically when you do multi-threaded, when the hardware also supports multi-threading. Let's take an example of calculating pi. Uh, I'll share this code also with you so that you can readily take and run it. But let's understand how I can calculate pi, the one that you did using OpenMPI. how I can do that also on the same machine, not using multiple processes but multiple threads, right? So the kind of lower level way of doing this, if you know C programming, right, and the more mature threading library, older threading library came in C. You can also use Java threads and so on, but essentially the concept is the same. So if I use a pthread is what we use for in C programming to create threads. Uh, so the structure will be something like this, right? You have to essentially go and say that here is my loop where I will uh, kind of parallelize each iteration of this loop essentially will run an independent thread. So for I is equal to 0, I less than num threads. And then I have a core function that I want to start a thread for. So here I have essentially created a thread for the function compute pi. Compute pi is my core function that actually does one kind of slice of the computation, and I'm running this in parallel. Same thing for matrix multiplication, right? This could be the dot product, and you have two loops, right, for doing the row and column, and within that you kind of start threads. So let's go back to the example here. So I would basically write a create thread inside this loop, right? And the dot product is basically the function I have to write, which will get called from each thread. Same concept here, except dot product I'm calling compute pi, and I'm doing a create thread using the pthread library. So pthread underscore create is the same thing as a generic create thread that I wrote in my pseudocode earlier. But also you notice that I have to know when the threads finish and kind of finally I do the reduction, kind of join together everything and give the result. So here you must have a join, right? Create thread is like a fork operation, like you're branching off threads. So in this part of the code, you're starting off bunch of threads, right? Here you have started a bunch of threads. All the threads finish and they have to come somewhere and join up like a almost like a barrier synchronization, right? You to stop and join everything and give the result. So this is the piece. So there is an iteration which loops across all the threads. So if I've created 10 threads, I must call 10 joins. That means each time I am actually calling this pthread underscore join, giving a thread ID and saying, I'll wait till that thread finishes. It is nothing but saying that let me wait till pthreads I finishes and then I will proceed. So when all these threads finish, then I can exit this loop. And as you see that as I'm joining, that means each thread is finishing, I'm taking some result from that thread and I'm kind of creating my final result. So total hits is going to be my final result. I'm taking the partial results in the hits array with index I to take for the ith thread. Now, this hits I is actually the hits data structure is common to all the threads, right? This is shared memory. So if from a certain thread I want to access any element of the hits array, I can easily do that, right? So the point is if you have shared memory, any thread can access this global variable. They can all access it, except we are being very nice to each other by only updating our own entries. So for example, here I'm only updating in thread I, the ith entry. I could have written a bad piece of code where I update some other entry. So it is not safe. So always you should make sure when you write multi-threaded code, you are accessing some shared memory, shared across all the threads. Don't make a mistake in programming where you modify data unknowingly or maliciously or because of some error, whatever, right? So you have to be careful. Now, this is not easy. As you see this, I have explicitly written a parallel program using pthread. Now, it provides some speed up. It has hardware portability because pthread library is supported on all sorts of hardware. Same as many other threading libraries. It's good support. It does good amount of latency hiding because different threads will run asynchronously. When some does CPU, another does memory access, another does IO. So they'll work very well to hide all sorts of latencies in the system, give me good parallelism. But now imagine the complexity of this code for you to write, right? And then there could be problems that you have to address. Just as I said, don't make the mistake of modifying data that you are not supposed to modify. So make sure there is mutual exclusion. Like if you're going and accessing some shared data structure, make sure you lock it and only one thread can go and modify it. So we'll come to some of those examples, but there's a concept of critical sections where you want to kind of lock things and not have two threads modify the data at the same time, right? So locking has to be there. Has to be some kind of synchronization using barriers. I talked about barrier synchronization earlier. So you have to make sure that when two threads are progressing, maybe there's a condition you have to do where one waits for the other. And then there's a whole problem of thread scheduling. Now, all these threads, let's say you have created 100 threads and you have an 8 core machine. How do those threads actually run uh, on those 8 cores? As a programmer, often you will have to put in some sort of scheduling because you know your logic better, right? So often these threading libraries will ask you to tweak some parameters in terms of scheduling for getting better performance. Like when I parallelize uh, the whole matrix multiplication, should I take certain chunks of the matrix and then divide it up statically among all the threads? Or should I do it dynamically? Should I give the uh, half matrix to two threads and let them kind of further start subdividing dynamically all this work between some child threads? I mean, it's complex to figure out what is working better and modify your code accordingly. So this becomes very complicated coding and you have to keep modifying your code for doing all of this. So there must be a simpler way out. So imagine you have sequential code to calculate pi and I want to convert it into parallel program without going through all this trouble of using pthreads or Java threading libraries and so on. That's where OpenMP comes in. It's a standard again. Uh, it's a it's a mechanism of sort of kind of avoiding the tedious or explicit thread management that some of the lower level threading libraries bring in, where you have to write more code. And if you are not an expert programmer, you will end up making mistakes, right? So let's assume a case I was saying matrix multiply. Let's say I already have some code to do matrix multiplication sequentially. Sequential code is ready. I know that there's a loop inside, right? I was showing you code earlier where we were calling dot product. So there was a nested loop. I know for sure that that loop can parallelized. Now, if I want to take that loop and modify that code to make it parallel, that conversion is actually quite mechanical. It can be automated. Now, the question is, can I do something so that uh, there is that multi-threaded code automatically gets generated without me writing that multi-threaded code? Can I put some annotations or remarks or comments kind of thing on my sequential program so that I give hints to the compiler and the compiler creates multi-threaded code? Is that possible? That's actually what OpenMP does. So OpenMP is nothing but a set of compiler directives. Compiler directives are like hints. It's like comments you put in your code, not for the end users or other developers, but for the compiler. So the compiler knows what you're trying to do, and the compiler will do additional code generation. So OpenMP is nothing but a specification for compiler directives implemented by the C language. There are other languages also which might have this kind of directives where it can go and generate multi-threaded code if you put in these directives in your sequential code. So automatic parallelization. It's an open specification of multiprocessing. So let me show you. So Java programmers also have something like JMP. Python programmers have something called Cython. which have this specification support. So if you are a Java Python programmer, I don't think any of you are Fortran programmers. You can explore OpenMP. Definitely C. So my examples I'm sharing are in C. So you can go to this website and check out a little bit more, but let's take some examples that will make it clearer. So it's portable, right? You can implement incrementally one function, one loop at a time, because let's say you have a big sequential program. Now, instead of spending the entire effort writing new code for a parallel program, what you could do is you could take one piece of your sequential program, one loop, and insert some OpenMP directives, and only that part will get parallelized. So incrementally, you can work on parallelizing your sequential code. Again, these are some instructions so that you can try it out. Uh, if you are using C, GCC 4.2 above supports OpenMP. Essentially, what you do is take your program, and when you compile your code, put this flag OpenMP, and automatically the any directives you put into this code will be kind of processed. Similarly, look at Java and Python as well. You should be able to find similar mechanisms. And when you run this code, right, once you compile with this OpenMP and that a.c code gets parallelized, you can essentially run it with and change number of threads on the fly. I'll share code with you to know how to do that. Uh, OpenMP's execution model is basically this. Imagine this to be your code, right? You have some when you start your function, you start your program, the main master thread. There's only one thread in the beginning until you hit some kind of a create thread or necessary to fork into multiple threads. This is your parallel region. End of a parallel region, you must always have a join so that all of the results get combined into one single thread again. Again, a fork will happen, again, a join. So it will be like your program is nothing but a sequence of parallel regions and sequential regions, right? Till the program ends. So it's basically a fork join model of parallel execution. Now, what does a directive look like? So I will also pull up some code example increment. Let's go through a few of the slides and I'll pull up a code example. So a directive is something like which you insert in your existing code. Let me go to some piece of code actually and show you first so that it's clearer. See, do I have some code here? Yeah, so same the pi computation code. Let's look at this. This was originally a sequential program, right? Uh, all what I did was I inserted certain directives here. I want to tell the compiler uh, where all some parallelization can happen. So here I've put in a directive. We'll go into what these mean. I've put in a directive to tell the compiler that look, this piece of code where you are basically going through a loop and multiple steps, you can potentially parallelize. So in C code, hash pragma is what the directive is. So whenever you put a comment hash and put a pragma after it, the compiler knows this is a comment for me, for the compiler. And what type of directive is an OMP or OpenMP directive. And what you're trying to do, you're trying to parallelize, right? And what you're trying to parallelize, you're trying to parallelize the next for loop. Ignore this piece for now, reduction, private, and so on. But essentially, I'm telling the compiler, look, the next for loop that you see, you can please unroll it, and each of the iterations you can actually run in parallel without me writing any multi-threaded code, right? So this is the core how I can go and parallelize it. Okay, let's go back to the directives. So essentially, an open directive will, as I was saying, it will basically have a hash pragma OMP. It will be the name of the directive, what is the directive we're giving, and give some clauses, some optional clauses or parameters to that directive. For example, I could be saying parallelize this for loop. And by the way, when you schedule it, this is the scheduling policy you should follow. Or inside the for loop, this is my global variable I access. So if you take the example again, you notice that I have put something called private X. This is kind of an additional clause. I'm telling the compiler that look, you can parallelize this. So for I is equal to 0, I less than steps. So I'm saying that if steps is 10, then you could potentially run 10 threads. And each of those threads are actually using a variable called X. And I'm telling the compiler, look, X is actually a private variable. That means it is not shared across threads. It is a thread has its own copy of X. If I give this hint to the compiler will automatically generate code where each thread will actually treat this X as a local variable. Whereas if I say public, then they will all share the same variable and keep updating it. For example, it could be that sum is a public variable. Actually, I could put here public sum. Right? That's something I could be doing. So this is a list of clauses I put in. So, so the clause list is basically specify some conditions of parallelization. It can say number of threads, some data handling like private, public. Uh, it can, so I could even put kind of conditional parallelization. I could say if some logic is there, some scalar expression, like I can say if uh, num equal to 10, then only do this parallelization, otherwise don't do it, right? Or if steps is less than 100, then try to parallelize. But if steps is more than 100, don't parallelize. I could put in those conditions. I could specify how many threads I want to run. So even though I say parallel execution of the for loop, I can say don't do more than 10 threads. And as I said in data handling, I can say private and shared and so on. There's something interesting called first private, which is very similar to private, except it's basically giving you some initialization value. So think of that pi code again. I said private X, but if I said first private X equal kind of 10 X 10, then that essentially means that X should be initialized with 10 for the first time in each thread. So there are many such ways to tweak around and create, kind of give hints to the compiler how to create a multi-threaded program. Uh, so ultimately what happens is a pthread kind of code only that gets generated. So think of a sample OpenMP program like this, right? I have a main function, I have some serial segment of code. Then I put in there was some parallel segment here, some for loop or something that I want to parallelize. So I simply put a comment here saying that hash pragma won't be parallel and give some clauses like I want to run this parallel segment in 8 threads. And by the way, a variable A is mentioned in this parallel segment, that is a private variable, which means that A should be copied in all the threads, that each thread has its own version of A. And by the way, the variable B is shared. So all the threads, when they modify B, it's a shared copy. And then whatever happens within these brackets, whatever code is there, that segment is automatically parallelized. Now, when the compiler works with this, it can generate something like this code. It will ultimately generate a lower level pthread library code, but you don't have to write it, right? So think of the mapping here. This particular thing, pthread create, pthread join for 8 iterations, all this was inserted by the compiler. You did not have to go and do all this work. Because imagine now I want to run this for different number of threads, or I want to change a few things here and there as parameters. I can do it in one place. I don't have to touch my core code. The core code remains the sequential code that I wrote, just that it automatically gets parallelized internally, right? So it becomes a lot easier in terms of code management. So general code structure is like this. Again, these are for you to kind of do some self-reading. I want you to write some sample OpenMP code. Uh, Maybe take my the pi computation code I will share with you today. Look at that and run it, and then you can modify it, right? To and you'll notice all these pieces there. A note about the private and shared variables. We already saw that, but essentially, when you declare something as private, it's a local copy. You see this? It's a local copy per thread, and whenever you say something is shared, it's like a global version. So everybody modifies it. These arrows are nothing but the threads executing. I will, Veena, I think you mean some live code. Yes, the Pi code I will actually show you so that you absorb this and then I will show you the full Pi code running, if that's what you mean. But I think identify these clauses, know what these clauses mean so that you can find them in the code and you make sure you understand how they work. Uh, this is another example of the shared and private. So in this particular loop, so there's a nested for loop. I want to parallelize this, right? I want to essentially run this in multiple threads without me writing p threads or some Java threads kind of code where I explicitly declare threads and do joins and so on. So all what I do is I put a hash pragma directive on top, and internally this piece of code will get parallelized. And I'm specifically telling on top that look, these are my shared variables and these are my private variables. By the way, any loop index is considered private by default. It is not to be shared across threads. So even if this priv index, which was a loop index, I had not specified in private, even then it would have been automatically taken as private. Let's go to the reduction clause. Then we'll kind of let's after this we'll probably go to the pi example and take a deeper look. But let's take a look at the reduction clause, how it will work. Yeah, Veena, I think I will talk about that, how deep you need to go. I think if you the slides I'm going through and the code that I will share in Pi computation, if you understand how that limited set of directives, how they work, and at least the understanding is there that how are shared variables declared, which are the private variables, I think that level is good enough. I don't think in this course you'll be asked to write large scale multi-threaded code. Neither you are going to write very large scale OpenMPI code. Uh, the assignment is the only place where you will go and write practically some OpenMPI code because, and I'm not asking you to write OpenMP code there as well. Uh, at that level of complexity is good to get familiar, but I don't think beyond the directives, there are many more. Beyond the few things I'm showing here, you did not go deeper and become an expert in OpenMP or OpenMPI. But this is just to kind of so that you understand that when you are writing a data analytics application, you understand two levels of parallelism. One is OpenMPI, which is helping you to do message passing systems by building multiple processes and executing on a cluster. Second is when you have one cluster node and your multiple cores, multi-threading is the way to speed up that program and gain some parallelism on one node. Now, whatever you're doing here may be an introduction to this. Uh, But when you write production code, you have to go a lot deeper and make sure you know how to write multi-threaded and multi-processing code. But this is an introduction to show you that look, when you're running large-scale data analytics, you have to look at these two levels and learn some languages and libraries to write these kind of programs. And you will encounter issues. So what happens to most people is you may not be in a job role where you write this kind of a program, but You may end up using a Hadoop or a Spark, but know for sure that the Hadoop and the Spark actually are implementing all of these under the covers, right? So they are the experts who probably go deep and build the middleware level so that you are happy writing the analysis function, but not focusing too much on how do I write the core parallel processing part. And the reason why OpenMP is being brought in is showing you a mechanism where if you are not an expert developer writing multi-threaded code and you have sequential code, you can simply give some directives I'm mentioning here and have the compiler generate some parallel code that makes your life simpler. Okay. So this is another uh, kind of directive for reduction, right? In OpenMPI, we saw reduction. Even OpenMP, which is multi-threading, not multi-processing, even here there's reduction. When you, it'll be interesting when you go and study MapReduce in Hadoop, you will hear the term reduction there as well. So reduction is nothing but how do I bring things together across multiple processing contexts? How do I get all the data together, apply some operation on it, and make it a single value? That's what reduction means. You will see that in OpenMPI across processes. You will see that in MapReduce, in Hadoop, Spark, and all the systems. As a programming paradigm, when you do reduction, you will see that in OpenMP as when I want to combine results across threads and present one value. So instead of writing all the code, I can simply give a reduction operator. And that essentially means that, look, you calculate all this local things inside each thread, but when you finish, then add up all those local sums into one big global sum and give it to me. That's what reduction means. So just like in OpenMPI, there were a bunch of operators. In OpenMP also, there are a bunch of operators like add, subtract, multiply, and so on. Right? So these are your operators. You will find them very similar to what in OpenMPI at a process level was there for reduction. Here it's at a thread level in a shared memory system. Reduction operator. All of this is to reduce your coding. So here is a reduction clause kind of in action. These are, you can go into some of these examples. Uh, let's see if there's anything else that is interesting in terms of what you should know about. So here are some little bit of optimizations. I think here uh, I would encourage you to look at this syntaxes little bit so that without uh, kind of you don't have to really go and apply this in writing big programs. But I only thing I want you to understand is know what each of these mean. So when I give you a use case, you can at least say, okay, oh, I heard about this no wait primitive and I can use that, right? So think about the usefulness of each of these compiler directives, at least that much, not necessarily going and actually writing code with this. So imagine this case, right? I have some code segment where I want to parallelize this loop and the next loop. Now these two loops, if you notice, are fairly independent, right? So the first loop is actually calculating B and array B from array A. And the second loop is calculating array D from array C. If you see some code like this, that means you immediately know, look, these are independent, right? So when I parallelize this, let's say I first parallelize this part because I've written here hash pragma OMP4, which means it will go and parallelize this piece. However, while I'm parallelizing this and running, I don't want this second loop to wait. Let's say I have 100 processors and I've distributed this array A and B. This piece is loop across this 100 processors to calculate B. Let's say one of those processors finished computing one index of B. That processor is free now, right? It's finished one of those indices. Rest are remaining, but one processor finished. Should I wait for the entire B to be finished before I move to the computation of D? That's a waste. So what I could do is that processor that became free from the computation of B can immediately be allocated to the computation of D, even though that code comes later, but it's independent. So OpenMP has a mechanism for the user to also hint to the compiler saying, look, you can do this, so don't wait. So no wait means as you finish this code and as different processors finish executing different threads here, don't wait, allocate that thread and processor to the following piece of code. Just keep moving as you finish. You don't have to, everything doesn't have to finish here for the entire computation of B across 100 processors for all the 100 indices of B before you move to the next step. This is a great optimization, right? Now you can say the compiler could have guessed. The compiler can analyze this and say, oh, D and B are independent. Yes, true. There are a lot of these parallelizing compilers who are intelligent enough to do that. But here is a way for the programmer to also hint to a standard C compiler saying, look, you can uh, do process allocation, a processor allocation this way, right, without waiting. So at least get these concepts of where I can optimize a little bit, use what kind of OpenMP directive. That at least introduces you to some basics of parallel programming without saying that, okay, let me write a full program using no wait and make it high performance. That's not the expectation from you. But at least identify these. Where are they useful? So if I give you a piece of code without giving the primitives, the hash pragma directives, you can suggest, look, this piece of code can work better if I have a no wait. There's also a section directive. Essentially, not everything is a for loop. So a section directive basically says that I'll simply put that this section can be task one, this section can be task two, right? So you're basically helping the compiler identify blocks of data, blocks of code that can be allocated for different tasks. So task one, task two potentially can run in parallel uh, by specifying these sections. This is an example here of OpenMP section, right? So this is one section, this is a second section. Okay, let's look at another interesting piece where we talked about barriers. Remember I talked about in OpenMPI how you do barrier? Uh, exactly same is here. So there it was barrier synchronization across multiple processes. Same thing, here it's across multiple threads. So you'll find so many things common between these two. One is doing at a process level, one is doing at a thread level. Both have to work in a single system because you will run a big application using multiple processes. Within each process, you will use multi-threading to give you the next level of speed up. So here, if you look at the code, I'm calculating an array AI from B and C. And then I'm calculating an array D from A and B. Now, I must finish calculating the entire array A before I proceed to the next step because D depends on A. I have to finish computation of A first, right? That means if I parallelize this part, let's say I'm running this, let's say n value is 100, 100 element array. I have 100 processors, so I can do this in parallel, right? 100 processors each can compute a value of AI. However, all those processors, even in the finish, I can't move a processor to the next step because I must finish computing all of AI, right? I is 0 to 100. Otherwise, processing of D will not help. So if I put a barrier here, that means all these 100 threads, when they finish, some will finish early, some will finish late. Once they all finish, then only I will proceed to the next step. Simply if I put this OMP barrier here. So the compiler will generate code with the appropriate lower level threading libraries to make sure that each thread comes and blocks at a certain time, at a certain point, uh, and wait for all others to finish. When all the 100 threads finish, then only it will proceed beyond this. So you can easily put a print statement here, and you will. So you can do one thing. You can take code like this and put a print here, print I, right, and put some print all done here. What will happen is each thread will finish and say print I, right? So you will get prints of 1 to 100, right, at different points in time. But you will not get this print all done before everybody is finished. When all are done, they together will cross the barrier and everybody will print all done. You can do this experiment and see. Okay. So second loop doesn't start before A is fully computed. Next interesting directive is OMP critical. Like, so you don't have to write code to define your critical sections. So imagine this piece of code. So you're iterating and you're incrementally building up a sum. Now, if you do this multi-threaded, right, uh, then what happens is, so everybody will be, each of the threads will be modifying sum in their own way, right? And depends on who runs first. There'll be simultaneous writes happening on sum, and the sum value will actually get messed up. So you cannot really parallelize just by running this code and saying OMP parallel for 100 threads. You can't run this. You'll get garbage. Each time you run, you'll get a different sum value because each thread will try and modify a global variable like plus something, but depends on what that sum value is at that point of time. Now, the way to kind of avoid, even though sum is a global variable, the way to avoid this random access and all that, you can actually do OMP critical, which means only whatever is within the brackets, only one thread can access. So you can have parallel processing here. You can have parallel processing here, right? Before and after this hash pragma critical, all threads will simultaneously do work. But moment you have OMP critical, this section, only one thread will get access to it. So two threads cannot enter and go and modify sum. That way, you will always get a consistent value of sum at the end. If you do intermediate prints, if you do a print here of sum, each run, you are likely to get different values of sum, different sequences, because in different runs, different threads will come in. But if you do a final print of sum here, that will always be the same because end value will be same no matter in what way the scheduling of threads happen. So this critical section definition is also something you could do in OpenMP. Again, you see that you're not generating any code. You're just telling the compiler, look, this is my critical section, and just make sure whatever threads you create, only one enters at a time, right? You're not introducing locking methods and all that code you're not writing. It's the compiler that is generating all of that. Here are some just environment variables. Okay, let's talk about one last thing here about scheduling. This is also something that you as a programmer, you should know that you could control for thread management. So schedule is a special directive, a compiler directive where you can tell the compiler that generate code so that the way threads get scheduled, I'm able to control. And there are certain predefined scheduling classes. So I'll give you a brief outline of what these are and why do you need them. So static, dynamic, guided, and runtime, right? So think of a program that is basically uh, doing again some kind of matrix manipulation, right? It's a matrix multiplication loops, and this is your sequential program. This is the sequential program you have written. You can run this on your laptop, one core machine without any threading, and it'll work. Now somebody tells you parallelize this. So what would you do? You would simply put a hash pragma directive on top saying uh, hash pragma OMP parallel, right? This whole section and default private. That means anything I don't define as a variable as This is considered to be a private variable, and these are my shared variables a, b, c, and some variable dim, right? That's my shared variables. And by the way, I want to run this using 4 threads. Ignore this for now. Ignore the schedule for now. So if you run this, automatically this will be partitioned into 4 threads. A, B, C, and dim will be considered as global variables shared across all the 4 threads. And anything else like I, J, K, these will be considered as private variables by default. And they indeed are, right? They are local copies of the threads. Whereas the actual arrays ABC and this size of the array dim is what a shared variable is. All threads should know these values. So automatically this will be parallelized. If you have a 4 core machine, you will have 4 threads running and it will finish in 1/4 the time, ideally. Now, how are those threads going to get scheduled? If you say static, what it means is the compiler will pre-decide what will thread 1 run and when what work will thread 2 have, what work will thread 3 have, and so on in advance. It will just partition the whole array and give it to these 4 threads, and it will run in that exactly same way each time you run the program. That's static. So essentially, think of the iterations you are doing in your program. It's a three-dimensional array, right? IJK. You could be slicing up work among the processor, among the threads in various ways. Uh, just 3 examples are shown here. I could have taken this three-dimensional structure and I could have sliced up where each of the threads get each of these slices. Look at the diagram A, right? I could have sliced up my array of size 128 into 128, and I could have uh, kind of made 4 partitions out of it, and each partition I could have given it to a thread to work on. Or I could have done a different slicing like this. Or I could have done another kind of slicing like this, right? In BC. So basically it's data partitioning. I could do it different ways and give that work to different threads. Question is, will it yield different results? It will, right? Because it depends on how threads get scheduled on the processor and how much work they have. Can you do static only? Not necessary. I can also do work dynamically. Now, matrix multiplication is an example where you can very well estimate how much time it takes. It's very regular work. But there are many other cases where you may not be able to estimate. It's good to do a dynamic behavior, right? Adjust as you go along. So here's a diagram that kind of shows you that if I dictate using the schedule clause how to schedule these threads, what will happen? It's a diagrammatic way of showing you. So imagine this x-axis is time. It's like the iteration number as it progresses. And the y-axis is thread ID. So there are 4 threads, right? 0, 1, 2, 3. And I've shown you 3 cases here. The bottom one is static. The middle one, the green one, is dynamic. And the top one is called guided. Now, the simplest one, static, essentially says that you basically divide up your work, right? All these iterations. So I'm sorry, the x-axis is not, it's not time, it's basically the iterations. It's how many, is I to j into k, the number of iterations you have to go through, right, for the full matrix multiplication. So what I could do is I could say, well, your first 150 iterations or 125 iterations belong to thread 1, next 125 iterations belong to thread 2, and so on. So I evenly partition the 4 iterations. It's like separating out all the data into these 4 threads and saying, now you go ahead and do the work, right? So that's one way of allocating. The another way of allocating is purely dynamic. So I could say that, well, each thread, let it dynamically pick up work, let it grab 5 iterations at a time and work on it. And whenever it is done, let it pick up the next 5 iterations. So since the 4 threads are running in parallel, each time you run it, each thread will randomly pick up 5 iterations. Let's say the first 4 slots of 5 iterations each, the 4 threads will pick up here. And then they will finish at different times, right? Because you can't synchronize all the threads. They will finish their work at different speeds. Whenever one is done, it simply picks up the next five, and so on, right? And you can change this number. You can say dynamic 50. In that case, it will be coarser grained. So each thread will pick up 50 iterations at a time. Whenever they finish, they pick up next 50. The chunk size. If you reduce your chunk size to small numbers, that means the scheduling overhead is more, because each time a thread picks up work, there has to be some synchronization and scheduling overheads, right? But you'll get a finer grained parallelism. See, in the static schedule, it's not a fine grained parallelism. You have statically defined work and given it. Now, if one thread messes up, nothing can be helped. You cannot reallocate that work to anybody else. But in dynamic, you have the every 5 iterations or 50 iterations, whatever you define, you can make another decision to say what work should I give to this thread. So if a thread is slow, it will get less work. If thread is fast, it will get more work. So it will balance out in the system, right? So this is great. But only thing is, if you want to grow your chunk size, you'll have the usual problem of scheduling over it is less, but then you can only make that decision after 50 iterations are complete. If a thread is slow, you can't quickly decide and take away work, right? So there's a downside to that as well. So you have to balance. A mix of this static and dynamic is an interesting one called guided, which essentially means that you first give 1/4 of the work to somebody. Then instead of giving equally 1/4 to the others, you keep giving 1/4 of the remaining part. So when you allocate to thread 0 1/4 of the work, 125 iterations, the next one maybe is thread 3, you give it 1/4 of what is remaining, not 1/4 of the full. So you see it's kind of diminishing gradually, right? So then when one of the thread finishes, it'll pick up whatever is 1/4 of the remaining, right? It'll keep going like this. Uh, that way, it's kind of the mix of both. You're not really doing static. You're starting with sort of a large chunk, and then you're gradually reducing the number of chunks to a minimum like 5. So that's another interesting way of doing scheduling. I mean, people do a lot of work in changing scheduling policies and seeing for their workload what works fast and all that. But as long as you realize that one can do such things for a parallel program, it should be good, right? Just understand that these are tunable things. And in OpenMP, you can give a schedule directive, and you can say, I could have put here not static, but I could have said guided 5, right? And you could observe, does it change your performance? Does it finish faster, right? You could do some experiments. Uh, again, takeaway here should be that know some of these directives and what's the concept behind them. Why do I need it? Uh, I don't think you will not get coding assignments to come up with complex code of for using these, but I'm happy if you know what these directives mean. And if I give you a code segment, you can say, well, I could be introducing this directive here, and that will make it better, right? So that kind of understanding you should have. Okay. Uh, so we have 15 minutes. We spent a lot of time on the programming part. I have not gone through the pi example in depth, but I will share it. What I want you to do is look at the pi example in OpenMP and in pthreads. I will share both and look for some of these directives, right? So that you can interpret that code. You can run it. I'll give you instructions to run it and you will see the output. You can change number of threads, the schedule, you can experiment. Okay, now given 15 minutes, I don't think we should run too fast through this. We will spend some time in the next class covering some designing of parallel programs. Let's see at least let's see some of the primer stuff. Let's cover some parts of it and then take it up in the next class. In the meantime, if you have any questions on what we covered, why don't you bring it up, put on chat. We'll take a pause for 30 seconds and wait for any responses for what we covered till now. Okay, if not, let's go ahead. Uh, this deck, which I will share today, I have not shared it already. Uh, Essentially, now gets into, well, at least you can look at some code, run it. Uh, in the assignment, write something with the OpenMPI. You'll get a flavor of parallel programming, but it's good to think about conceptually what are the problems you will encounter in writing a parallel program. And this you will see while you're doing your assignment. And let's talk about some of those, right? What does it take to create a parallel program? Essentially, the what you're trying to do is primary thing is to speed up, right? You want to make sure that you get some kind of speed up as you increase number of processors or cores. If on the same machine you're getting more cores through multi-threading, you can speed up. If you have multiple nodes, through adding multiple nodes, you're able to get a speed up. So can I get whatever time I got with one processor? Can I divide that significantly if I put P processors, right? We'll see later when we study some of the laws, which will tell you that look, time by one processor and time taken by P processors is this ratio is not P. Ideally, it should be, but it will never get to P. You will never get speed up of P processors. Yeah, 10 processors can't be 10 times faster. It won't happen. But anyway, as you're achieving this speed up, your main goal is to get a higher efficiency. You want to work with bigger problems that can fit on a machine, right? Or multiple set of machines. So as you think of a parallel program, essentially you should think about it is in these steps that will happen. Not you're not in control of all the steps as a programmer or as a designer of your parallel program. If you're like solving a large data analytics program, you may not have control over the parallel machine which will run it, but at least you may have some control over how do I decompose the problem, right? That may be something that you may have control over. Give me 1 second, one moment. Okay. So the first step is decomposition, right? We'll look at various, this is probably the most important step from a programmer standpoint. Like how do I break up my problem into parts? So we'll talk about some kinds of decomposition here. In fact, we'll spend another session later in this course talking very deep about decomposition, problem decomposition. Now, and after decomposition will come assignment. Assignment means how do I assign work to different threads or workers or processes, whatever way you want to call it, right? You may have heard this term called workers in different cluster systems. So, how do I assign work to a software entity that will execute that work? So, some decomposed partition should be taken up by some worker and it should process it, right? The next step after that is called orchestration. Orchestration means that these workers have to kind of be coordinated. They don't work independently. For example, I need some data to be sent from worker 1 to worker 5. Maybe this reduction operation is happening. You will see when you're writing your first parallel program in OpenMPI, think of it in these steps: decomposition, then assigning to a particular process, and does that process need to communicate with another process to send data, right? Or control messages. That's orchestration. And finally, mapping is uh, probably not in your control all the time, right? So mapping means how do I take this particular uh, set of processes that are communicating and how do I map it to my hardware, to my parallel machine? That often will be done by some lower level entity and you may not have that much control. Now, each of these steps, these responsibilities may be done by the programmer. The higher you go, decomposition, assignment may be in some programmer control, or it could be the control of the system, like the compiler, runtime, hardware, or it could be both, like the programmer can give hints and influence the system, right? What to do. Just like we were giving hints in an OpenMP program saying, oh, here is how you should schedule, right? So, but please be aware of these 4 steps because when you're designing a program, you have to think about the four steps, and the fourth step may not be that much. Mapping may not be in your control. It depends on where you're running things. But decomposition definitely is. So problem decomposition key idea is, how do I identify dependencies or lack of dependencies? Like, you identify what's independent of each other. Can I break up a problem into tasks, right? And I should at least have enough tasks to keep all my execution units busy. So if I have bought a machine which has 100 nodes, I must be able to decompose my problem in a way that it needs at least 100 machines, at least 100 partitions of the problem. Otherwise, I'm wasting resources, right? So you have to break it up, keeping the machine in mind. How many nodes do you have, and can you keep all of them busy? And another key challenge in doing that is, are the dependencies. Because if you have a dependency, then you cannot run things together. If A depends on B, then you have to run B and then come to A. You cannot run them in parallel. So it's very critical to identify dependencies between nodes. Otherwise, you will not be able to, uh, or dependencies between tasks or problem kind of elements. Otherwise, you will not be able to effectively parallelize it. This, typically the programmer is responsible for it, right? And automatic problem decomposition of sequential programs, it is a research area. It's pretty difficult in the general case. Often you need programmer hints. You already saw the example in OpenMP, where we were giving compiler directives to say, here is a for loop. You can run this in 8 threads. Now in a for loop, maybe automatic is okay. Even if I have not given the directive, the compiler may have figured out that I could parallelize this loop, but that's a specific case. In many other cases, a compiler may not be able to automatically figure out, right? Uh, because there are key issues, like you may not know all dependencies, and some dependencies are very data dependent, right? You don't know whether two tasks are uh, dependent on each other unless actually at runtime you see the data. So you don't know at compile time. However, if you look at this loop nesting and all that, loops are ideal examples where you could easily parallelize, right? So all these parallelizing compilers are out there, but often they need user hints. What we just discussed in OpenMP is a set of hints we are giving the compilers that it can write parallel code without me bothering about it. So we'll dig deeper into decomposition as we go along. When you talk about assignment, as I said, it's basically about assigning things to workers. So you have to uh, think of tasks as the kind of stuff that you do, like, and the threads are like workers, and you have to say, okay, I have to calculate a max of bunch of numbers. So which worker thread should I give it to? That's basically assignment. And the key problem you're trying to address there is balancing workload and reducing communication costs. Remember that in a parallel system, the best way to get efficiency is when the system is balanced. If there are 100 nodes and two nodes are lagging behind and 98 are working, that is no good, because you will wait for the two nodes to finish. So assignment is a big deal to say, how do I balance workload? How do I spread workload across my machine? So you have done a good decomposition, but maybe your assignment is not good. You have assigned certain decomposed partitions into machines, which is not occupying all the machines uniformly. Hence, you will still get bad results or bad performance. So decomposition is important, but assignment is also very important. So although programmer is often responsible for decomposition, often the runtime or the language that you use, they take responsibility of assignment. The programmer may not know at runtime what to do, right? So the programmer responsibility drops after decomposition. Programmer can still give hints. And as I said, during scheduling, you are giving a hint as a programmer, right? But the assignment of how threads pick up work, that could be done statically, could be dynamic. It depends how the programmer hinted, right? So think of the scheduling we talked about of threads picking up work as something like an assignment that the programmer kind of can hint. Orchestration is primarily about communication. You can see the diagram, right? It's basically about a bunch of communicating workers who are exchanging data so that something can get accomplished. So the key problem there you're trying to solve is, how do I reduce communication cost? How do I preserve locality of reference? How do I reduce overheads? The biggest killer in a parallel program, even after you've done effective parallelization, is huge amounts of communication happening between nodes, which means you have very low locality of reference. So you don't end up using local data, you keep calling another machine and shifting data around. And this causes a whole bunch of overheads and often leads to poor performance. So we'll study this again in depth around mid-sem, I mean, after a few sessions or right after mid-sem we will study, but how do you measure all these overheads of orchestration? There's some formal kind of ways to kind of study that. And of course, machine details impact a lot of this, right? It very pretty much starts getting very hardware dependent. And the final step about is mapping to hardware. Uh, I'll give you some examples here. So mapping can happen at various levels. So this is what we call mapping, right? You take all these communicating workers and you're trying to map them to different parts of your physical machine. Now, this could be done in various ways. Often you could do that in the operating system itself, right? Mapping a thread to a hardware execution context on a CPU core, like your multi-threading example, right? That could be done by the OS itself. It could be mapping done more statically by the compiler. So essentially, the compiler can figure out, look, I can partition data in a certain way, and I can put this data on 4 nodes. You can statically put that in during compilation. So to exploit data parallelism, we'll talk about data parallelism going forward. So compiler can do it. The hardware itself can do it. If you look at a lot of the GPU systems, uh, you can the GPU cores. Uh, the CUDA thread blocks, and CUDA is a library used for writing GPU based applications. It was written by NVIDIA and then made open source. Uh, it is used for writing very with the hundreds of cores of in GPUs. Then you can use CUDA to kind of do that parallel processing. So mapping a block of threads in CUDA to a GPU core, that can often be done in hardware because it's a very large scale. So you don't have software, you have hardware to do all that mapping. But as you go through this, there are this mapping part is quite interesting, even though it's kind of not in the control of the programmer really, but compiler, operating system, hardware. But it's interesting in the sense that without knowing much about or without getting much influenced by the programmer, how do you actually place these software pieces on hardware blocks, right? Is it that you place communicating threads or cooperating threads together on the same processor? Because that will maximize locality, data sharing. It will minimize communication, right? If two threads are communicating, you might as well put them on the same processor because communication costs will reduce. However, a counter theory could be that if things are unrelated, maybe put them on the same processor. I could do that as well. Why? Because it is possible that I will use the machine more efficiently. Like while one thread is doing CPU, another thread will do IO, right? In that way, one I could take a bandwidth limited or a network intensive job and put it on the same machine as a compute intensive job, and I can use the machine more effectively. That's another school of thought. So it's a hard problem to solve, this mapping piece, especially when you are not able to take programmer hits, right? Uh, so these steps, be aware of what each of the steps do, and what we will do going forward is we'll pick it up in the next class. We'll start looking at designing a parallel program. What can happen automatically, what can be manual, how do I understand the problem and start kind of doing some sort of decomposition. We'll get deeper into this whole partitioning, right, in the next class, and different ways to partition problems. The slide deck will be out there, so you can start looking it up, reading, and We'll start on the same page in next session. But please start thinking about your assignment along these lines of designing a parallel program, right? Decomposition first and communication and all these aspects you should start thinking. All right, we'll stop here. And any other questions? Okay, then I'll meet you next weekend and have a good weekend.